Okay, challenge science. Okay, so this gets into a little bit with how gases dissolve in liquids. And this goes in, so we're looking at the solubility of a gas in a liquid, and it gets into polarity and pressure. So this is really important. This will finish off like our solubility, molarity discussion. I posted some answers to some of the molarity problems. I tried to pick like 2 on each page with a variety so you understand, you know, how to do these problems in different ways, and there are little conversions you needed to do. So they're posted. You're going to continue to do nomenclature review. And, you know, Thursday, we're going to get into the cell membrane structure, which is really cool. And that will set us up to, once you understand the cell membrane and the basics, I'm not getting into the high level stuff. That's more for next year, but you're going to be really familiar already. And that cell membrane stuff is going to help you for next year. And so we'll get you ahead in bio too a little bit. But we're also going to talk, and you're going to see how it applies with polarity. Polar likes polar, nonpolar likes nonpolar. And then we're going to get into soap, how that works. And then we're going to talk about soap in the coronavirus, which is really relevant. So interesting stuff. So pay attention. This is really important. Okay. So this diagram right here talks about soda. In soda, you've got one of your components is a gas. It's carbon dioxide. It's nonpolar. Okay. We know it's nonpolar because it's linear. Both sides have the same number of excess valence electrons, so those two negative ends tend to cancel out. Down here you got water. H2O has the IMF called a hydrogen bond. You understand that already. And I know I don't like this drawing too much because it really doesn't show a squiggle right there. Like, they don't really differentiate here between a chemical bond and an IMF. So ultimately you would draw a box around this, and that negative oxygen is kind of attracted to that positive H. Okay, again, I'm not a big fan of this drawing, but I think you guys should understand it. So it's like, this is a molecule attracted to this molecule. This water is attracted to that water. This water is attracted to that water. So you guys should be really familiar with that by now. Okay, so again, water, we'll take a look at this. 2 hydrogen atoms, polar. We know that. It's sticky. It involves itself in cohesion. That's the IMFs. Adhesion, it can stick to other things like glass and other things that are polar. Okay. So, under normal conditions, can CO2 dissolve in water? A little bit, but not necessarily. But here's the thing, though. Because it's a gas, they're very active, and they can easily break. So watch my mouse right here. So pretend you're a gas, and you're going like around. Remember we did in the hall, we were running around like a gas, like a dumb gas. Okay, get rid of the G. Okay, so if I'm a gas and I'm this mouse, hopefully you can see my mouse, and I'm trying to get through here. If I'm going around, I can easily break right through that. Again, break right through, because I have a lot of energy, and I can overcome those IMFs. And right here, you see this gas molecule right here, leaving and right out there, overcoming the IMFs. Okay, so again, look how it's written. The activity of the gas overcomes the bonds. Well, I'm going to say the hydrogen bonds, meaning the intermolecular forces, not the chemical bonds. They're not breaking the H2O molecule. Notice, look at the mouse. The H2O molecules are still kind of together. This is a physical change. All it's doing is breaking the IMFs, the intermolecular forces of attraction. You need to understand that. So what do we do to kind of trap the gases in there? So watch this with the gas, solubility of a gas now, not of a solid in a liquid. We said before, if we want to get more solid, like sugars around here, we need to heat up these water molecules so they spread out to surround more sugar that wants to be in there. Think of that for a minute, because it's polar and polar. How do we convince a non-polar thing that has a lot of energy to stay in there? Well, if we cool down the water, the solvent, what happens? The IMFs become stronger, and you learned that back in October. Okay, so right now we're dropping the temperature, and as a result, it's going to take more energy. Watch the mouse for the gas to escape and get out. See, if it's kind of warm, it's easy to overcome these IMFs and leave. If it's cooler, it's going to be harder to get through those IMFs. So how do you increase the solubility of a gas in a liquid? Drop the temperature, reduce the energy. Therefore, it can't escape as fast like it wants to because it's energetic and it's nonpolar. Okay? So you want to drop the temperature. That's one way. So when they make the soda, to keep the CO2 in there, it still is going to escape, just not as rapidly. But they're going to drop the temperature first to slow it down. Okay. Then what they do is, check this out, they increase the pressure. So to increase the solubility of a gas in a liquid, you drop the temperature to slow it down from leaving, and you, bam, increase the pressure. Force that in there. Almost cursed. And again, it's my house, so I want to curse. I'll curse whatever I want. Pressure is increased. So what happens? More CO2 is crammed into the water until it's super saturated. So we've added so much more. More is dissolved than possible. And they're running out of room, so they're kind of trapping the CO2 from leaving because the IMFs are really, 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 really strong. And it's forced in there, and that's why they seal it shut. So what happens, so again, let's go back to the review here. To increase the solubility of a gas in a liquid, you want to drop the temperature, reduce the energy so it can't leave as quickly, okay, because it wants to leave. Again, gases are less dense than liquids. What else do you want to do? Force the crap load in there, make a supersaturated solution, force it down and lock it in, pressurize it. Okay, so so then you have two 2-liter bottles of soda. One has been in the refrigerator overnight, one is sitting there. Open them both up at the same time. What do you hear? Which one is going to go flat? Well, what's flat soda? Soda that no longer has carbonation in it. So if you let two 2-liter bottles of soda, so bottle A was cold in the refrigerator overnight. Bottle B, warm, room temperature. Open them up. You know, they make that noise when you open it up, comes out. Which one's going to go flat first and why? Well, going flat means gas is escaping. Well, which one would go flat first? The one where the gas can escape easier, or would it be more difficult to escape? The one that will go flat first is the warm one. Why? Because these molecules have more energy and it's easy for these CO2 guys to escape. Whereas if you have cooler soda, they'll still escape, but not as rapid. That's why colder soda takes longer to go flat. So here, all we did was take the following, because before, quick review, to increase the solubility of a solid in a liquid, right? You want to increase the temperature of the solvent to accommodate more solid to stay in there, because it doesn't want to like rise and leave, right? What about a gas? Well, pressure has something to do with the solid. What about a gas? Well, it wants to leave anyway. So two things you want to do: drop the temperature, reduce the energy so it can't escape and break through those IMFs as quick, and then pressurize it, force it down in there and lock it in, okay? And then think of this too. When you pour a soda, do you want to pour a soda from really high? What happens? You pour it, boom, all that kinetic energy, max GP, pour the soda from up top. Max GP, there's more of a max GP, more KE. If more KE hits the glass, what's going to happen? That's why you get a lot of fizz and it what? Escapes. That's why when you want to pour a soda, bring the bottle lower, tilt the glass. Do this at home. So the lip of the bottle where the soda comes out has the smallest amount of movement from the bottle to the glass as possible. So when the soda comes out, right? Comes out, hits the glass, there's minimal GPE, minimal KE, the soda won't fizz as much. That's all it is. It's so relevant, all this stuff. So that finishes off mostly solubility of a gas and a liquid. So make sure you pay attention to this and take notes. This is very, very interesting. Okay, I'm going to hit stop share and I'm going to hit stop record, and we have another video coming soon I'm making.